In this brief lesson, we're going to just look at what a horizontal stretch is when we're talking about transformations of functions. You should already be familiar with vertical stretches. Think about quadratics, where you know the a value gives you a vertical stretch. And horizontal and vertical shifts, those would be the h and k values when you're talking about quadratics from your grade 10 course. So you may have wondered why there's no horizontal stretch if there's a vertical stretch, and it turns out there is one. It's simply that in grade 10 you didn't talk about it. It was probably considered a little bit more advanced than where you were at that point. So now we're going to go back and talk about what the vertical stretch looks like. So in this form, y equals f at kx, it's just, we're looking at, that's a general form for any function, just saying we've got a relation, it's a function. The k value that you can see here is going to give us a vertical stretch, sorry, a horizontal stretch, pardon me, horizontal stretch. And just like vertical stretch, it can be a stretch or a compression, so it could make it wider or less wide, and it can reflect the function as well. It would do it across the y-axis. Think about, again, compare it to a value, the vertical stretch and reflection. Remember, a gives us two things. It gives us the vertical stretch, and it also gives us the reflection up or down. So I'll call it a vertical reflection. So it reflects, the a value reflects across the x-axis. So you should know this. You know, you may need to think about what I'm saying for a second, but you've learned this before. So k value, instead of being vertical, everything's horizontal. It gives the horizontal stretch side to side, and it reflects it in the y-axis. Again, a horizontal reflection. If the k value is greater than 1, we're going to see a compression. So let's just pause for a second. If the k value is greater than 1, we're going to see a compression. That's different. For an a value, the bigger the a value was, if we had an a value of 2, it was vertically stretched. It was twice as tall. What we're saying here in k for horizontal is the opposite. We're saying that if k is, say, 2, it's going to become less wide. It's going to be compressed horizontally. And if k is between 0 and 1, in other words, that was supposed to be a highlighter. If k is between 0 and 1, then we're going to see a stretch. So again, that's opposite from what you've seen for the a value. So if we had an a value that was, say, 0.5, we know that our parabola would have been compressed down half as tall. K value, if we have a k value at, say, 0.5, it's actually going to become twice as wide. So everything about k values as far as the stretching goes is opposite to a. Right? Maybe instead of putting it in quotations, I'll say opposite to a value. If the k value is negative, we're going to see the reflection over the y-axis. That's the same idea as if the a value is negative, it's just over a different axis. And the reason, or the way this works is because instead of multiplying our x value by the k value, we're going to divide the x value by the k value. So if I start with some point, x, y, and I try to compress it, or I try to horizontally stretch or compress it, whatever the k value is, I'm going to divide that x value by k. So let's look at some examples. Given f at x equals x squared, graph each of the transformations listed below, state the domain and range. So here's our parent function, and it's going to go up forever, of f at x equals x squared. So in this case, we can see that there is a k value of 2. First of all, how do I know this is a k value? Well, this is k because of where it is. Maybe, actually, I even need to take a step back for a moment and explain what does this f bracket 2x mean? Let's interpret that for a second. We're being told that f at x equals x squared. So f at x is our basic function, and then what we're being told down here is if we take our basic function, we want to stick a 2 into it. So if our basic function is x squared, then we're being told to put 2x into our basic function. And so we're replacing, again, that was supposed to be a highlighter, we're replacing x in f at x equals x squared with 2x squared. So again, it's using the function notation just to substitute things in. So this is the equation that we're asked to work with. Now, what I was trying to point out is that we can tell that this is a k-value because of where we see this value. K-values are always inside the function. That's how I like to describe it. What do I mean by inside the function? I mean that if there's brackets or something going on with the function, it's right in there beside the x. It comes in front of the x, but it's inside the function. Compare it to this. Y equals 2 and then x squared like this, where the 2 is on the outside of the brackets. That's an a value. So we recognize different transformations, whether they're a or k, by where they are. So this one being inside the function means that it's a k value. Okay, so what? So based on what we saw above, we know that if k is greater than 1, it's going to be compressed. So we're going to expect this quadratic to become more compressed horizontally. It's going to become skinnier. How much so? Well, it's going to be compressed such that every x value on the original function is going to be divided by k. In this case, k is 2. So every x value is going to become half as wide. So let's take a few x values. Let's look at this one here. So if we just look at 0, 0, then the x value is 0. If I divide the x 0 by 2, then I get 0 still. So it turns out that this point doesn't move. But if I start with, say, this point, 1, 1, if I divide this x value by 2, now I'm going to get a point 1/2, comma 1. So I'm going to get a new point that's at 0.2 on the x-axis, sorry, 0.5 on the x-axis, and 1. And if I go to this point here, which was 2, 4, I'm going to divide that x by 2, and that, of course, becomes 1. The y-coordinate will stay the same, and so I'll have the point 1, 4. And so I can go all the way along this quadratic, picking any point I want, and then dividing the x-coordinate in half, and it's just going to move all the points in closer to the y-axis, and the same thing's going to happen here on the left side. If I had the point -1, 1, then I'd divide that by 2, and I'd get -1/2, 1. So I'd get a point here, and then I'd get -1. You know, see, once you pick up the pattern, you can see what's going on here. So if we look at this graph I've done here, this is the graph of y equals 2x in brackets squared, because the k value of 2 made it half as wide as the parent function of y equals x squared by comparison. So that's how k-values work. So a k-value that's bigger than 1 is going to become skinnier. So a k-value of 2 will make the parabola half as wide. A k-value of 3 would make it 1/3 as wide because I'd be dividing by 3. A k-value of 10 would make it 1/10 as wide, very skinny looking because we're dividing by 10. So what happens if I have a k-value that's between 0 and 1? Well, we've already been told that it's going to get wider. Let's see why. So again, just understanding the function notation, we're told that f at x, remember f at x equals x squared. So putting this together, I'm going to plug that in here. Y is equal to 1/3, I'll put 1/3 x in for x, and I get 1/3 x squared. And guess what? Now I've got a k-value of 1/3. So again, think about that mapping formula we had above. By mapping formula, I just mean the one that says xy becomes x over k, comma y. So I'm always dividing my x coordinate by the k value. So again, in this case, k equals 1/3. So again, let's take some points. If I take the point 0, 0, then literally I'm going to have 0, well, I guess I could do it over on the graph like I did before. Literally, what I'm going to have is 0, the x-coordinate, divided by 1/3. But we know 0 divided by anything is still 0, so that point doesn't move. What about this point? Again, 1, 1. If I divide the x value by 1/3, that's really awkward to see 1 divided by 1/3. But remember, dividing by 1/3 is the same as multiplying by 3. So 1 divided by 1/3 equals 3. 1/3 goes into 1 3 times, doesn't it? So my x value becomes 3, while my y value stays the same. So having this k value of 1/3 is making my x's, my whole graph, spread out more, 3 times as wide. And we can predict that for the point 2, 4, it's going to become 3 times as wide, and it's going to be 2 divided by 1/3, which is the same as 2 times 3. So I get a new x value of 6. And then the one that was 3, 9, if I multiply, so I can just do a short form now, right? Instead of dividing by 1/3, I know that multiplying by 3 is the same, so I'll just multiply my x value by 3, and I get the 0.99. Again, the y value isn't changing. The k value, k does not affect the y value of a quadratic. Same thing's going to happen on this side, right? I'm going to have 1/3, 1, but I'm going to multiply my negative 1. Sorry, why did I say 1/3? I'm going to have negative 1, 1. I'm going to multiply my negative 1 by 3, and I'll get negative 3, 1. And so I'd get a point over here. And it's just going to keep happening like it did on the other side. And here's my new parabola. And as you can tell, it's much wider than the parent function, which is exactly what we expected. And so this is, how did I write it above? Y equals 1/3 x squared. But again, that 1/3 has to be in the brackets to be a k value. That's not the same as 1/3 x squared like this. If I write it like this, then that 1/3 is an a value. Again, k values are recognized by where they are. They're inside the function. Keep that term in your mind, inside the function. So in this case, I mean inside the function as in it's inside the brackets. The 1/3's inside the brackets, isn't it? Which means that this squared is affecting it, whereas the 1/3 I'd written down here is not inside brackets. The squared does not affect this 1/3. So there is a difference. Inside the function is going to make it be a k value. All right, so our last example for this little lesson, we know that in this case we're substituting negative 1/4 x into f at x, and so then we get negative 1/4 x squared, since f at x again is the parabola y equals x squared. The k value in this case is negative 1/4. Remember what the negative means. It means it's going to be reflected in the y-axis. That was supposed to be straight up and down the y-axis, although I missed. Anyway, it's reflected in this y-axis. It's like we're using the y-axis as a mirror. Now, if I had an asymmetrical function, then that would make a bigger difference than it does in this case. But since the y-axis, since the parabola is symmetrical but the y-axis, if I reflect it in the y-axis, I'm going to get the exact same parabola, aren't I? So in this case, we're not going to see much difference because of the fact that it's negative. In fact, we're going to see no difference by the fact that it's negative. But let's go through the steps anyway, just like I did before. So 0, 0 divided by negative 1/4. Again, 0 divided by anything is still just 0, no change. So that point stays the same. But this point, 1, 1. If I divide 1 by negative 1/4. Well, dividing, let's forget about the negative part for now. Dividing by 1/4 is the same as multiplying by 4, right? So it's going to get 4 times as wide. But I'm also changing to a negative number, so it's going to reflect that point over onto the negative x-axis. So it's going to become 1 divided by negative 1/4 becomes negative 4. So that point there is going to go all the way over to the left side. And this point, which is 2, 4, if I divide that by negative 1/4, again, that's the same as multiplying by negative 4. I'm going to get negative 8 for my x value, and the y value is going to stay the same. And then I've sort of run out of room. Well, what happens to the ones that are over here negative to start with? I'll do that in a different color just to differentiate. Well, that one starts as negative 1, 1. If I divide the negative 1 by negative 1/4, the two negatives cancel out, making it positive, and I'm still multiplying by 4, so I'll get this point, that point that started negative ends up over on the positive side. So you can see how it becomes a reflection in the y-axis. The points that started on the left side, because of the negative sign, are being turned positive, and the points that started positive are turning negative. So likewise, this point, which was 2, 4, negative 2, 4, will be multiplied by negative 4. It becomes positive 8, 4, and I get that point over there. That's how the k value works. And so then I just connect my dots, and because the k value is quite small, it gets made very wide. So, k value, what I need you to take away from this lesson is that k value is a horizontal stretch or compression, but it's the opposite of what you'd expect. The bigger the k value is, the more compressed the shape is going to become. When k value is between 0 and 1, it's going to actually become wider. And the closer to 0 it is, while still being positive, it's going to become wider still. And a negative k value is going to reflect it in the y-axis. And although, again, in this case, because it's a parabola, that didn't make any difference. But we're going to transform other graphs where it will make a difference.